Okay, guys. Let's talk about what we're doing today. This is kind of this experiment. It's not like any other experiment that we do throughout the year. And I can't remember if I said there's not going to be any math in this class. If I did, I lied. Because in this lab, there's some math. And actually, in another one, there's some statistics, but it's not too bad. So, and I really like this lab because we're going to learn about a bunch of different things. If nothing else, then it's a really nice introduction into extractions. And extractions is a really important concept in organic chemistry in particular, and other chemistries as well. What we're going to be dealing with today is methyl violet. And this is methyl violet. Okay, sorry. So that's methyl violet. And we're actually going to be dealing with aqueous solutions of methyl violet. Okay? And you guys learned a rule, or I think you've learned a rule. Have you learned a rule yet about solubility? How to look at an organic molecule and decide, is it going to have some water solubility? You guys learned that rule? Yeah? Rule of 5. Dr. Organ,
I think he started it, but he didn't finish it.
Oh, okay. You know what? I'm going to start it, finish it right here. It's not very hard for rule of 5. So, what rule of 5 is, so nitrogens and oxygens are what help an organic molecule go into water, be soluble in water. All right. Now, how do they do that? Because they can hydrogen bond with water. Even like this nitrogen, you may not, oh, it doesn't have an NH. Yeah, so it can't donate an NH for hydrogen bonding with water, but it can receive an H. This lone pair can get close to the H on a water molecule. Okay? So we call that a hydrogen bond acceptor. It can behave as a hydrogen bond acceptor in that sense. Okay. So the rule of 5 is, all right, we know that oxygens and nitrogens are important for water solubility. So if you look at an organic molecule and you count all the oxygens and hydrogens, okay, you can have at most carbon, I'm sorry, I should preface this, that carbons hurt water solubility. Okay, they're not carbon hydrogen, they're not really, it's not a polar bond, okay. And the most global rule of solubility is like dissolves like. Water is very polar, carbons and hydrogens are not very polar. So carbons, you can think of it simply as carbons hurt solubility, oxygens and nitrogens help solubility. All right, so for every nitrogen and oxygen, you can have at most 5 carbons. Okay, so according to that rule, what's the maximum number of carbons that this molecule can have if it's going to be soluble in water? Here's where the math comes in. Anybody? How many nitrogens are there? 3. There's 3. So for every nitrogen, or oxygen, but we don't have oxygen. You can have at most 5 carbons. So what's the maximum number of carbons this molecule? 15. But if you count them up, it's got much more than 15. Okay? So technically, it would break the rule of 5, and we would predict, if we were looking at this thing, we would predict no solubility in water. Yet today, we're using it as an aqueous solution. It's quite soluble in water. It's also soluble in organic solvent, that you guys are going to find out, but it's also soluble in water. Does anybody, and this definitely may not be anything that Dr. Horgan has explained to you, but does anybody want to stretch out your brain and come up with a conjecture as to why this is soluble in water, even though it doesn't obey the rule of 5?
Because it's ionic?
Bam, bam, crushed it, out of the park, right out of the bat. Not even a pause, yes. Yes, water loves ions, sodium chloride. Most salts, I mean, we did learn some in Gen Chem precipitation rules. We learned some salts that aren't soluble in water, but in general, water loves salts. It loves ions. The H's of water can gather around the chloride, or the anions, and the oxygens of water can gather around the cations. Okay, so it loves salts. This molecule, if you remember, we call this a polyatomic ion. Okay. Many atom ion. So it's a salt. So salts, if it's a salt, it can help you break the rule of 5, and indeed it does. Nice job. Okay, so we're going to be dealing with this is methyl violet, so let's just abbreviate that ME, right? Okay, we're going to be doing something in a very basic sense, similar to what we were doing last week. We're going to be examining this with UV light. What do we say makes a molecule absorb UV light?
Double bonds?
Yeah, specifically alternating double bonds. If you just have an isolated alkene and there's no other double bonds anywhere near it, not really going to absorb UV light terribly well. Okay, so we got our light source again. UV light source. Okay. And here's our sample compartment. And then some light will go up right on through. And we've got to detect. Okay. We're going to be using spectrophotometers, or the common name for the ones that we're using are called spec 20s, I believe. Okay, so, and the solutions that we have in here, they're going to absorb light to varying degrees, okay? Now let's think about some of the things that would make it cause, sorry. I'm going to put just a little bit of coffee, and I don't really need that much, but I didn't. All right.
It's Monday.
Yeah. Okay, so let's think about some of the things that would cause a solution to absorb light less or more or less. Okay. Can you think of some things?
Concentration.
Concentration, exactly. I have a super cheesy example that I always use. Pardon me. Okay, if this is the compartment, the sample compartment where the solution is, and pretend I'm light, and I'm running through and I'm trying to get to the other side, what are the things that are going to, and if I bump into a molecule that's got alternating double bonds, I'm UV light, it's going to absorb me. So what are the things that can affect my ability to get through the sample compartment? Concentration. The more concentrated it is, the more likely it is that I am going to run into one of those molecules and be absorbed. Okay? So, the faculty support center, I tell you guys this, they just got purple. And I'm like, Pathetic how much it excites me. Okay. So, absorbance is proportional to concentration. Okay. All right, what else? What else is going to affect whether I can get out that other end and get to this detector without running into a molecule that's going to absorb me?
The length of the cell.
The length of the cell. Bang. Second one out there. Yeah, I mean, it's just a really basic thing. The longer this path is, the harder it is for me to get to the other end and get out. Okay, so the length of the cell. Directly proportional to length of cell. Okay. And then it's also, you know, it's not independent of the molecule. It's going to be affected by the molecule as well, right? I mean, if we've got a molecule that's got two alternating double bonds, it kind of absorbs UV light. This thing's got double bonds all the way, you know, all over the place. Okay, so it absorbs UV light much better than another molecule that might just have two alternating double bonds. Okay? So if we're thinking about the different factors that are going to affect absorbance, you need to take into account what's in the solution. What's the specific chemical that's in the solution? Okay? And that one is called molar absorptivity. We symbolize that with an epsilon. Right? Okay. And that changes for every molecule. Okay. And it turns out because we have this, and it's a constant for every molecule. Okay. Whatever the value is of this for methyl violet, that's the value it is for methyl violet all over the world. Okay. Because that's a constant, we actually can combine these proportionalities and change them into an actual equation. Okay. All right. I really have a hard time breathing in this thing and talking. If I collapse, you guys just throw some cold water on me. Okay? Only if I collapse. Don't like if I look like I'm going to collapse. All right. Okay, so we can do that. Okay. Because that's a constant for each compound. That's a constant. We've typically, and this will be a constant for your experimental situation as well, I should mention. I mean, it's the length of your cell path is the length of your cell path. Okay. We tend to use the same value of this. Okay. So this tends to, I'm looking now. I think what we tend to, almost always, most machines are designed so that it is a unit of one. I think it's 1 centimeter blanking, but I'm 99% sure. That's 1.0 centimeters. Yeah. That way, numerically, it won't affect your values, right? It's just multiplying by 1. Okay. All right. So, you can almost discount that when you're sort of examining the form of this equation. Okay, that's a constant, and that is a variable. That's our independent variable. This is our dependent variable. So dependent variable equals a constant times independent variable. What does that resemble? The equation of a line. Science folks love this. We feature this all the time. Oh, actually, I should have wanted that better. Sorry. So this is sort of mx plus. Okay. All right. So what that means. Now there are 4 parts to the experiment today, so I'm just going to go over each part real briefly. Any questions so far? They never asked that. So it's like in the teacher bullshit. Alright. Part 1. Okay. the first thing you're going to do is, in part one, you're going to determine epsilon. Okay? And the way we're going to do that is we are going to this is in molarity, okay, concentration in capital M. Okay. There are 4 standard solutions that have been prepared for you. They're back in the booth somehow or another. They're placing and spacing things differently than they used to, so they're back there. Okay, and they are they're very carefully made at very specific concentrations. And then you're going to measure the absorbance of these 4 different solutions. Probably going to be a lot cleaner than that. How I drew that. Let's try this nicer. So you're going to measure your absorbance. You record that data. You go home and you put it into an Excel spreadsheet, okay, or any spreadsheet software that you want to use. And then if it's Excel, you come out here and you ask it to add a trend line. Okay, make sure you're not connecting the dots. Okay, you don't want to. All right, you want a best fit linear relationship. Okay? You should include in your data 0, 0. Okay. We want to do this assessment based in part on the idea that if there's no methylviolin in there, there's no absorption. Okay? So 0 concentration, 0 absorbance. All right.
Do you care if we put absorbance on the y or x-axis or concentration on the y or x-axis?
Well, I mean, since absorbance is your dependent variable and concentration is your independent variable, I mean, you could still do it, but let's see. So
No, that makes sense because there's a convention for that.
yeah.
And it also says in the directions that the x-axis should be the concentration and the y should be the absorbance.
Yeah, I was actually trying to think of what the line would look like if you did it that way. Anyway, yeah. For the time being, just do it this way, and then. Okay, so you get your best fit line. You tell Excel or whatever you're using, please add a trend line, best fit line. Okay. When you make your plot, that's a tip in Excel. That's called a scatter plot. All right. And then you ask it to add an equation. Okay. And so it will spit out, the real equation here. Okay. Now we found epsilon. How do we find epsilon?
The slope?
It's the slope. Yeah, exactly. Okay. You still may have a y-intercept. Even though you put 0, 0 down here, you still may have a y-intercept because when it does its calculations to do its best fit line, it may not intercept that even though you put that there. In my drawing, it did. But. Okay, so y is your epsilon. Let me just take a quick note. I think it's in the worksheet, but I can't remember 100%. If your epsilon should be in the thousands. Okay. That's how you're going to know you did it right. If your epsilon isn't in the thousands, if it's kind of a small number, okay, it's like in the single digits or less than 1, there's a mistake. In my experience, what that mistake typically is because the concentrations back there are in scientific notation, 3.4 times 10 to the negative 5. 5.6 times 10 to the negative 6. Okay. In my experience, what that usually is there's been a problem putting it in your Excel spreadsheet and sort of obeying scientific notation. What Excel uses to put in scientific notation is E. Okay, usually I believe, I don't know, Google it. It's an easy thing to Google. If it's still coming out funky and you can't work it out, then fine. Forget scientific notation and put it in Excel as 0.00000, blah, blah, blah. Does that make sense? So make sure that your epsilon is in the thousands, tens of thousands typically. Okay? All right. Rock and roll. Now, if you know epsilon, okay, you know that's 1. Now what you can do is you can actually take the absorbance of some random solution where we don't know the concentration and determine the concentration. Okay? And that's essentially what we're going to be using the spec 20 for part 2, 3, and 4. We're going to be using the spec 20s to figure out the concentration by measuring the absorbance. Okay? All right. By the way, if you didn't get a chance to print out the thing, I got these for you guys. So, how many people? Just out of curiosity, because I was thinking, how much should I print out? How many people need one? Need a printout of the thing? Okay, you too. Oh, okay. All right, cool. Where's my purple? Yay. All right, so. I may have screwed up my Roman numeral. Sorry if I don't have a Roman numeral 2. This is part 2. And in part 2, you are making your individual solution A. Okay? Making your solution A from the stock solution. So we've got a stock solution over there of methyl violet, and it doesn't say the concentration on there. Okay, it doesn't have it on the bottom. All right, and it's pretty concentrated, so you're going to make a diluted solution, but you're not going to do it very carefully. Okay, and I'll explain why I'm making that point. I believe you're going to take half a mil of the stock solution. You're going to take your graduated cylinder. You're going to add about 19.5. Okay, you're going to pour it in there. All right. So ordinarily, you're doing a dilution. Gosh, I gotta figure out what's on the bottle and then calculate for the dilution. But you don't care. You're not doing any of that. Why are you not doing any of that? Because now that you've made solution A and you have your epsilon. You can take a sample of your solution A, measure the absorbance, and because you have the epsilon, you can figure out the concentration, right? Okay. All right. So I'm going to put a squiggly. That's like ish. Determine ish concentration of solution A, your solution A, each of you got your own, from absorbance. Better than my ish sign, I should probably put a little asterisk right there. Okay. And what's the math? How can we do this? Well, I always, especially like when I'm teaching Gen Chem and stuff like that, I always suggest to you, or to students, rearrange equations before you plug stuff in for what you want, So we want concentration, so if you rearrange this guy for concentration, it would be absorbance over epsilon times length. Okay. Pay attention to the units of epsilon. It's the units of epsilon, this has no units, so this is 1 centimeter, and so this is going to have units such that you end up with moles per liter, concentration, molarity per liter. Okay? So think about that. It involves things raised to the -1. All right. Okay, but there's a wrinkle. There's a problem. It turns out that the solution that you make, when you take out the 0.5 from the stock and you add 19.5 and stuff, it's too concentrated for the machine. Okay, it's so concentrated, no light gets through, it just stops. Okay, you get complete absorbance, 0 transmittance. All right. So what you're going to do is you're going to take your solution A. All right. This time you're going to do a careful dilution. Okay, careful dilution. Right, so alright, and that's going to be 1.00 ml solution. Okay. Diluted to 10 mLs of. By the way, there's a lot of the procedure, the worksheet has a lot of subscripts and math symbols and stuff. This was originally developed by a faculty member who's no longer here, but he was a total math guy, so he loved. But they work out and they're helpful and stuff like that, so pay attention to them. So after you take your solution A and you take 1 ml and you dilute it to a volume of 10 mils, consider that solution A dilute. Today, by the way, is a good time to use one of my favorite lessons for working in a lab. Label, label, label. Label everything. It's all purple. All the not just the pen, but methyl violet is violet color. It's purple. So you won't remember. So make sure you label everything. Okay? All right. You're going to do that with volumetric flask. These are 10 ml volumetric flasks right here. So you put in your 1 ml, you carefully add type 2 water so your meniscus up to your line, all that good stuff. Put this on carefully invert it, blah, blah, blah. Okay. All right, now solution A diluted, you can measure the concentration. You can measure the absorbance, and then you can figure out the concentration of solution A diluted. Okay, but we don't want, that's not the ultimate goal. The ultimate goal is to find out the concentration of solution A. Okay? How are we going to figure out the concentration of solution A? That ain't wrong, but that's not what I was after. Okay, you may have learned this, and it rolls off the tongue better than the way I tend to do it. M1V1 equals M2V2 for that, right? If you know the concentration of either the diluted or the concentrated version of the solution, you know the parameters that were used to make to do the dilution, you can figure out the concentration of the more concentrated. Okay, so I tend to use MCVC, so that's the molarity of the concentrated times the volume of the concentrated equals the molarity of the diluted times the volume of the diluted. Yes? All right. Which one of these are the ones I'm after? If I want to rearrange this in terms of my variables, all right, which one do I rearrange it for? MC, molarity of concentrated, right? So
Wait, of the concentrate?
What's that?
Of the concentrate?
Yep.
Aren't we trying to get the one that we diluted? Like the one that we,
Yeah. That's
Approximately
the molarity of the concentrate,
uh,
right? We know the molarity of this, and we know that from measuring the absorbance, calculating the concentration, so we know the molarity of that.
oh, okay.
We want the molarity of that.